Hello friend, welcome back to your favorite channel. In the last video, that is heat transfer by means of radiation part 2, we had discussed some governing laws related to heat transfer by means of radiation. Now it is a time to solve the numerical based on the governing laws related to heat transfer by means of radiation. For the heat transfer by means of radiation part 1 and part 2, the links are available in the description box. Just refer that links and you can see the video related to introduction part of heat transfer by means of radiation and governing laws related to heat transfer by means of radiation. So today we are going to discuss about numericals related to heat transfer by means of radiation. So in this slide, you can see different laws and different equations related to heat transfer by means of radiation, absorptivity, reflectivity, transmittivity, Planck's law, values of constant C1, C2, irradiation, radiosity, and all these things. We had discussed everything in the previous videos. The links are available. Just refer these videos. This is very helpful to you for your regular as well as in the competitive examination. So without wasting time, let's start with the numerical part. So you can see the numerical. The following data relates to a heat transfer. The following data relates to the furnace used in the thermal power plant. So we are talking about the furnace that is available in the thermal power plant, and we are assuming the furnace as a black body. We are assuming the furnace as a black body. The temperature of the furnace is given 2773 Kelvin, that is 2773 Kelvin. We have to find out first part, that is monochromatic emissive power at 1.2 micrometer length. Second thing which we have to find out is the wavelength at which the emission is maximum. Third thing, we have to find out maximum emissive power. Fourth part, that is total emissive power. And fifth part, total emissive power of the furnace if it is assumed as a real surface with the emissivity equals to 0.9. So here in the first part, for first A, B, C, D, we are considering the furnace as a black body and we have to solve it. And for E, that is for the last task, we are assuming the furnace as a real body and emissivity of this real body, that is zero point 0.9, and we have to find out what is the total emissive power, that is EB of real body, EB of the furnace, that is of real body, we have to find out. So here important thing is given temperature is given in Kelvin. If it is given in degree Celsius, then again we have to convert that degree Celsius into Kelvin and we have to solve it. So now moving towards the solution part. What is given in the data? Temperature is given in Kelvin, wavelength is given in micrometer, and emissivity for the last case is 0.09. So now the monochromatic emissive power at 1.2 micrometer length, that is E lambda B, at lambda value 1.2 we have to find out. So E lambda B according to the Planck's law, that is equals to C1 lambda power minus 5 divided by exponential function of C2 divided by lambda t into lambda t minus 1. So here the C1 C2 value I told in the previous video also that you have to remember the value of C1 and C2, plus you have to remember what is the unit of C1 and C2 also. So here the value of C1 is available in terms of watt into micrometer power 4 per meter square. That we had convert this micrometer power 4 into meter power 4. So the value is available here. So now simply what we have to do is we have to put the value of C1 and C2 in this value of C1 and C2 we have to put in this equation. Plus we know what is the value of lambda and T. So everything is available in this equation. When we'll put all the values here, and this is the equation after putting all the values. So once we will put all the values, and when we will calculate, we will get monochromatic emissive power of this furnace, which we had assumed to be a black body. Its value is 2.014 into 10 power 12 watt per meter square. This is our first answer. Now, the second task is to find out the wavelength at which the emission is maximum, means we have to find out what is lambda max. So we know that according to Wein's displacement law, lambda max into T, that is 2898 micrometer into Kelvin. So when we divide this 2898 by temperature, we will get what is the maximum value of lambda. And that answer we will get 1.045 micrometer. That is the maximum value of lambda. Now we have to find out what is the maximum emissive power, that is E lambda B maximum. So simply what we have to do is we have to put this lambda max value, that is 1.045 into this bottom equation of E lambda B. So what you will observe is the maximum value of E lambda B, that is equals to 1.285 into 10 power minus 5 into T power 5 watt per meter square per meter length. So in that what we have to do is simply we have to put what is the value of T, that is temperature, in terms of Kelvin. So when we'll put the value in terms of temperature Kelvin, we will get the answer, that is 2.1 into 10 power 12 watt per meter square per meter length. That is the maximum emissive power. Where in this formula lambda max is already available. Now we have to find out what is the total emissive power. When we'll consider the furnace as a black body. So furnace is a black body. So EB, that is equals to sigma into T power 4. Sigma is Stefan Boltzmann constant 5.67 into 10 power minus 8 watt per meter square Kelvin power 4. Temperature is known to us 2773. So fourth power of temperature. So we'll get EB, that is the total emissive power of a furnace when we'll assume as a black body, that is 3.352 into 10 power 6 watt per meter square. Now in the last case, we are assuming furnace as a real body with the emissivity is 0.9. So now we have to find out what is the value of E, that is total emissive power of a real furnace body. So in that equation we have to add more term, that is emissivity, and emissivity is 0.9. So when we put 0.9 here, we will get the answer 3.017 into 10 power 6 watt per meter square. So you can compare the emissivity of a black body and emissivity of a real body. So friend, this is how we have to solve numerical related to heat transfer by means of radiation. I hope you understand this part. Let us try to solve one more numerical. So assuming sun to be a black body. So we are assuming sun to be a black body having the surface temperature of 5800 Kelvin. So you can see here the sun temperature is given, surface temperature of the sun, that is around 5800 Kelvin. That is the surface temperature. Center temperature is very high. So we are not talking about that part. We are talking about surface temperature only. We have to calculate the total emissive power, the wavelength at which the maximum spectral emissivity occurs, maximum value of E lambda b, total amount of radiant energy emitted by the sun per unit time if its diameter to be assumed as 1.391 into 10 raised to 9 meter. So for the sun, some data is available, like we can consider sun as a black body at present. Its surface temperature is also very high, that is 5800 Kelvin. Its diameter is also, you can see, that is 1.391 into 10 power 9 meter, and we have to find out four parameters related to sun. So I hope this data is very much clear to you. Let us try to solve this again. So here you can see the temperature is given in terms of Kelvin, that is 5800. Diameter of sun is given 1.391 into 10 power 9 meter. Now our first task is to find out total emissive power of the sun, that is EB. So when we'll assume it is a black body, we will get the equation, that is sigma into T power 4, that is according to Kirchhoff law. This is Stefan-Boltzmann constant. This is temperature value. So we'll get the answer, that is 64,200 kilowatt per meter square according to Stefan-Boltzmann's law. Now lambda max into T, that is 2898 micrometer into Kelvin. So we are again changing it. You can see micrometer into Kelvin is now converting to meter into Kelvin. So 2898 is converted into 2.898 into 10 power minus 3. So lambda max value is available, that is 0.5 micrometer. What is the maximum value of E lambda b? That is 1.287 into 10 power minus 5 into T power 5. So when you put the value of T as a 5800, we'll get the answer 8.45 into 10 power 10 kilowatt per meter cube. And the last thing, Q, that is sigma A into T power 4. So this is the solar radiant energy available, or you can see, refer the previous slide. So total amount of radiant energy emitted by the sun per unit time. So the total amount of radiant energy emitted by the sun per unit time, that is 4.38 into 10 power 26 watt. So this is the amount of energy released by the sun, and that is falling on the earth. So I hope you are getting it. So friend, in this video we had discussed about numerical related to heat transfer by means of radiation, and particularly the numericals are related to governing laws related to heat transfer. If you like this channel, in that case, do not forget to subscribe this channel, like this channel, and share this channel to your friends. In the next video, we are going to discuss about shape factor. Till then, have a nice day. Bye.